Picture this. You're standing 359 meters above a raging river, higher than the Eiffel Tower. Now imagine building a railway bridge at that height in the Himalayas, in one of the most earthquake-prone zones on Earth. India just finished exactly that. But this never started as a record-breaking project. The Chenab Bridge became the world's highest railway bridge because of where it had to be built. The height was the price of the location, and that location is where the real story begins. Let's talk about Jammu and Kashmir, one of the hardest places in the world to reach. The Chenab River cuts through the Himalayas, creating gorges so deep that for centuries, locals accepted some places couldn't be connected. Roads washed away in monsoons. Most engineers who looked at the gorge just walked away. The terrain here doesn't just challenge construction, it punishes it. The gorge. The Chenab River sits at the bottom of a valley so deep that standard bridge building techniques don't apply. You can't build supports from the riverbed up, the distance is too extreme, and the rock formations are unstable. Seismic activity. This region sits in seismic zone V, the highest earthquake risk category in India. Every structure needs to withstand tremors that would collapse buildings elsewhere. When the earth moves, everything you've built needs to move with it without breaking. Himalayan winds. Wind speeds here can exceed what most bridges are designed to handle. Forces that can lift vehicles off roads and tear metal structures apart. Temperature extremes. Summer heat reaches 45 degrees Celsius. Winter cold drops below -10. Steel and concrete expand and contract constantly. Materials that work in Mumbai or Delhi crack and fail in the Himalayas. For a very long time, Jammu and Kashmir remained partially isolated because nature made connection almost impossibly expensive. Roads closed for months during heavy snow. A single landslide could cut off entire districts. Medical emergencies became death sentences. Economic development stalled because goods couldn't move reliably. Without year-round, weatherproof transportation, the region remained vulnerable. When a region can be cut off by a snowstorm, it changes everything. How people live, how businesses operate, how the government can respond to crises. So the question became, how do you build permanent, reliable connections in a place that destroys everything you build? The answer turned out to be a railway bridge that nobody believed was possible. When engineers first surveyed the Chenab Gorge in the 1990s, their initial reaction was clear: avoid the bridge if possible. Tunnels seem smarter. Tunnels protect trains from weather. They're hidden from view, which matters in sensitive regions. And most importantly, tunnels don't require you to suspend hundreds of tons of steel and concrete 359 meters above a river. So they tried the tunnel approach first. The plan was to drill through the mountains, bypassing the gorge entirely. Work began. Money was spent. Engineers drilled into solid rock. And then they hit the problems: unstable rock formations. The Himalayas differ from older, stable ranges like the Appalachians. These mountains are young, still rising, still shifting. The rock layers are fractured and unpredictable. Tunnels that appeared stable on surveys often ran into sections where the rock was so broken that standard tunneling methods failed. Water. Underground water sources in the Himalayas don't follow predictable patterns. Drill into the wrong spot, and you're suddenly dealing with floods inside your tunnel. Controlling water flow at this scale, in these conditions, became a nightmare. Length. To avoid the gorge completely, the tunnel would need to be so long that travel time would increase dramatically. The whole point of this railway was to create fast, reliable connections. A tunnel that added hours to every journey defeated the purpose. After years of attempts and delays, the conclusion was unavoidable. There was no way around the gorge. The only way forward was across it. But crossing it meant building something unprecedented. Traditional bridge designs didn't work. The span was too wide, the height was too extreme, the geological conditions were too unstable. What they needed was an arch bridge, a design where the structure itself bears the load through compression, making it incredibly strong against both its own weight and external forces like earthquakes and wind. But arch bridges at this height had never been attempted for railways. Think about what this means. You're not just building a bridge, you're creating a structure that needs to support the weight of fully loaded freight trains, withstand earthquakes that would level most buildings, resist wind forces that could literally blow train cars off the tracks, function in temperatures that swing 55 degrees between seasons, last for at least 120 years with minimal maintenance. And you're building it in a place where getting materials and equipment to the construction site is itself a major engineering challenge. That record-breaking height of 359 meters came from necessity, not spectacle. It was the minimum height required to span the gorge while maintaining structural integrity. Go any lower, and the arch angle becomes too shallow. The physics doesn't work. The bridge collapses under its own weight. Go higher, and you're adding unnecessary cost and risk. 359 meters was the solution to an equation, not a vanity metric. Now let's talk about what it actually takes to build something like this. Construction began in 2004. The original completion target was 2009. It took until 2024, so 20 years to finish. That's not because of incompetence or corruption. It's because every single aspect of this project required solutions that had never been tested before. The wind problem. Typical railway bridges are designed so that trains stop running long before winds reach extreme levels. But the Chenab Rail Bridge itself is engineered to withstand winds of up to about 260 kilometers per hour in the gorge. At those speeds, wind does more than push against the bridge. It creates vibrations that can tear steel apart from within. The solution? A design called a cable-stayed arch that uses aerodynamic shaping to let wind flow around the structure instead of slamming into it. But that required wind tunnel testing at scales no one had attempted for a railway project in India. Engineers built scale models and tested them in facilities in Denmark and Japan. They simulated wind patterns specific to the Chenab Valley. They calculated the exact angle and shape of every beam to minimize resistance, so the bridge would be able to resist under extreme wind conditions. The earthquake problem. Seismic Zone V means this bridge needs to survive earthquakes measuring up to 8 on the Richter scale. But here's the tricky part. You can't make a bridge completely rigid. Rigid structures crack and collapse during earthquakes. What you need is flexibility, the ability to move with the ground without breaking. The Chenab Bridge uses something called base isolation technology, shock absorbers built into the foundation that let the bridge sway during an earthquake, absorbing the energy instead of fighting it. Think of it like a car's suspension system, but for a structure weighing 25,000 tons. Testing this required simulating earthquakes in laboratories. They built sections of the bridge and literally shook them with hydraulic machines that replicate seismic waves. Every joint, every bolt, every weld had to prove it could handle the stress. The precision problem. When you're building a bridge this size, precision matters in ways that are hard to imagine. The two sides of the arch were built simultaneously from opposite ends of the gorge. They had to meet in the middle with millimeter-level accuracy. Think about that. You're building two massive structures, each weighing thousands of tons, on opposite sides of a gorge, and they have to align perfectly when they meet 359 meters above a river. Any miscalculation, and the pieces don't fit. You can't just hammer them together and hope for the best. The engineering team used GPS-guided systems that adjusted in real time for temperature changes, wind deflection, and even the weight of workers on the structure. They calculated how much the steel would expand in sunlight and contract at night. They accounted for gravitational pull differences at different elevations. When the two sides finally met in 2021, they were off by less than 2 centimeters. The construction logistics problem. Here's something most people don't think about. How do you even get construction materials to a gorge in the middle of the Himalayas? There were no roads capable of handling the heavy equipment needed, so they built roads. Then those roads got destroyed by monsoons, so they built them again. Steel beams weighing 100 tons each had to be transported on trucks that could barely navigate mountain curves. Concrete had to be mixed on-site because it would harden before reaching the construction zone if transported from cities. Workers lived in temporary camps with minimal facilities. Medical emergencies meant helicopter evacuations. During winter, construction stopped completely because conditions became too dangerous. And through all of this, the project faced constant political pressure. Every delay meant more criticism. Every cost overrun meant more scrutiny. But they kept building. So why go through all this? Why spend over $500 million and 20 years on a single bridge? Because in certain places, connection is non-negotiable. Let me explain what rail connectivity actually means in a region like Jammu and Kashmir. Roads versus rail. The reliability question. Roads in the Himalayas are seasonal. Heavy snow closes them for months. Landslides block them for weeks. During the 2014 Kashmir floods, entire highway sections were washed away, cutting off hundreds of thousands of people. Roads in the Himalayas face constant pressure from nature. Heavy snowfall blocks high-altitude routes for long stretches during winter. Landslides bury sections of mountain highways without warning. Floods damage surfaces and wash away entire stretches of road. During the 2014 Kashmir floods, key highway links collapsed, leaving hundreds of thousands of people stranded and supplies delayed. Railways offer a different level of stability. Trains operate through snow and rain. Tracks sit on engineered foundations designed to handle extreme conditions. Once the line exists, it provides a year-round connection that holds steady through seasons that often shut down road travel. But here's the critical part. Railways move more than people. They move everything. Medical supplies can reach remote hospitals faster. Construction materials arrive in bulk for infrastructure and housing projects. Farmers gain reliable access to markets across the country. Military logistics gain speed and consistency in a region where terrain often slows movement. A single freight train can carry the load of around 50 trucks navigating narrow mountain roads. It moves that cargo in one coordinated system, with lower cost, fewer delays, and far greater predictability. Over time, that kind of reliability reshapes how a region functions. Businesses invest with more confidence, supply chains stabilize, travel becomes routine instead of uncertain. In a place defined by difficult terrain, dependable rail access creates a foundation for long-term economic and social integration. The economic calculation. Before this bridge, moving goods from Jammu to Kashmir meant either flying them insanely expensive or trucking them through roads that could close without warning. Businesses couldn't plan. Farmers couldn't guarantee their produce would reach markets. Construction projects faced constant delays because materials couldn't arrive on schedule. The Chenab Bridge does more than connect 2 points on a map. It makes the entire region economically viable in ways that didn't exist before. Industries that couldn't exist in Kashmir because of transportation uncertainty, now they can. Tourism infrastructure that was too risky to invest in, now it's feasible. The bridge creates predictability. And in economics, predictability is everything. The strategic reality. Let's not pretend infrastructure is politically neutral. Jammu and Kashmir is one of India's most sensitive regions. Borders are disputed. Insurgency has been an issue for decades. The central government's ability to move personnel and equipment quickly matters. A railway that works year-round means military logistics aren't dependent on road conditions. It means reinforcements can arrive in hours instead of days. It means the region can't be isolated by weather or sabotage. Some people call this militarization, others call it stability. The truth is probably somewhere in between. But what's undeniable is this. India decided that keeping Jammu and Kashmir connected was worth any cost, any delay, any difficulty. The bridge is the physical manifestation of that decision. Let's talk about the numbers everyone obsesses over. The cost, over $450 million. For context, that's more than the entire annual budget of some small countries. It's enough to build nearly 1,000 regular houses. It's the kind of money that makes government auditors nervous. Critics called it wasteful. They said the money could have been spent on schools, hospitals, rural development, and they had a point that money could have gone toward other priorities. But infrastructure goes beyond choosing between good options. It focuses on solving problems that continue to exist. Without this bridge, the railway connecting Kashmir to the rest of India was incomplete. Incomplete railways don't work. They're like building 90% of a highway and expecting cars to teleport across the missing section. The $450 plus million wasn't the cost of one bridge. It was the cost of making the entire railway system functional. The timeline: 20 years. Construction officially started in 2004. The bridge arch was completed in 2024. 2 decades. Governments changed. Engineers retired. Entire careers began and ended during this project. Why so long? Part of it was technical complexity. Part was the harsh environment. Part was political delays and funding issues. But part of it was something simpler. Nobody wanted to rush and get it wrong. If this bridge failed, if it collapsed, if a train derailed, if an earthquake brought it down, the consequences would be catastrophic, not just in lives lost, but in public trust destroyed. So, they took their time. They tested everything twice. They halted construction when conditions weren't safe. They redesigned elements that didn't meet specifications. The delays frustrated everyone. But the alternative was unacceptable. The persistence. Here's what impresses me most about this project. It was questioned constantly, but never abandoned. Every few years, someone would propose cancelling it. Too expensive, too difficult, too slow. And every time, the decision came back. Keep building. That kind of institutional persistence is rare, especially on projects this expensive and politically sensitive. Most mega projects that face this many delays get quietly shelved. The money gets redirected. The plans get postponed indefinitely. The Chenab Bridge could have ended that way a dozen times, yet it kept moving forward. In 2024, the Chenab Rail Bridge arch was officially completed. Trains begin crossing in 2025 as the full Udhampur-Srinagar-Baramulla railway line comes online. When it's fully operational, trains will cross the gorge at speeds up to 100 kilometers per hour. What used to take hours by road will take minutes by rail. The railway line that connects Kashmir to the rest of India will finally be complete. The engineering worked, the bridge stands, the trains are coming. So, success, right? Well, maybe. Here's the thing about infrastructure at this scale. You don't know if it worked until decades later. Will the bridge still be standing in 50 years? Probably it was designed for 120. Will it actually transform Kashmir's economy the way projections suggest? That depends on factors far beyond engineering: investment, political stability, how people and businesses actually use the connection. Will it reduce tensions in the region, or will permanent connection create new frictions? Nobody knows. Infrastructure shapes behavior in ways that are impossible to predict. The Chenab Bridge does more than cross a river. It permanently expands what's possible for the entire region. Travel patterns will change. Economic opportunities will shift. Strategic calculations will adjust. And all of that will unfold slowly, over years and decades, long after the engineers and politicians who built this bridge have moved on to other projects. The Chenab Bridge exists because India decided that leaving Kashmir isolated was unacceptable. Not just strategically, but fundamentally. Whether that was the right decision? History will answer that. But the bridge itself, 359 meters above the Chenab River, standing against earthquakes and Himalayan winds, is already answering a different question. Is it possible to build permanent connections in places where nature designed isolation? The answer, apparently, is yes. It just costs over $450 million, takes 20 years, and requires engineering at the absolute edge of what's possible. And that's where the story ends for now. If you think this bridge changes everything, wait until you see the next project India is betting billions on behind the scenes right now. Watch next India's $15 infrastructure gamble, what Delhi isn't telling you.